All right, so this is section 40142. Now, almost definitely there's going to be some conceptual questions in the homework, but this is the nuts and bolts of 40142. So weirdly enough, we're about to get into 4.3. Are you still in there? Yes. 4.3. Do you guys remember? Yeah, this is what I was talking about at the beginning of class. The problem where I said, what's the probability that you get at least one? And there were like 1,000,003 ways to do at least one. Okay. Take that out before I forget it. So let's do this. Even if I wanted to know the probability of one. So let's do a very specific example. Nice, concrete, freaking example, right? Let's say I've got 5 people. Right? And let's say we know that the probability somebody's left-handed is 11%. See if you guys are cool with this. Let's call it for short, we'll call it L. So left-handed person is represented by L. The probability is represented by L. It's crazy. So what's probably somebody's not left-handed? Why don't I just say righty? Because, somebody might not have any hands, and then they're not either one. So it's got to be all-encompassing, right? Now, of course, it's 89%, because that's what's left over. Yeah. Okay. Let's call that. Let me show you a symbol that I use. I think the book uses a little prime, but this symbol is what means not in probability events. Okay, so let's do this. If I have 5 people, and I want to know, we want to know the probability that we pick exactly one lefty out of 5 people. So I have 5 people lined up against the wall. I pick one at random. What is the probability that I pick a left-handed person? Stop for a minute. You guys all with this idea? 5 people. Let me see. No row has 5 people. Shoot. So I have 5 people lined up against the wall, and I'm going to pick one. What's the probability I get a left-handed person? So now I got 5 people, correct? What's one way we could do this? I got 5 people. Which one could be the left-handed person? First one. Okay. So the first one's left-handed, and the other 3, Jeff. The other 4 aren't. Right? You guys with me? So this would be the first one's left-handed, and the second one isn't, and the third one isn't. So if I wanted to calculate just this probability, what's probably somebody's left-handed? 11%, so 0.11. What's probably somebody's not left-handed? 0.89. I know, I'm getting there. We've done this kind of problem before. But when I asked you this question before, I was very specific. I would have said, so this would be if I would have said, what's probably the first person I pick is left-handed and the other 4 aren't, right? Okay, maybe. I think I said it wrong earlier, but it's all right. So if I choose 5 people from America, what's probably I get exactly one left-handed person. This right now is not the answer to that question. This is the answer to what's probably the first one's a left-handed person and the other 4 aren't. Why does that not answer the question, what's probably I get a left-handed person? Is this the only way I could do that? Give me another way.
Second person.
Second one. Give me another way.
There.
Give me another one. Wow, give me another one. Oh my God. You guys, how many ways is there to do it then? 5. Everybody see that, right? This list is relatively small because if I only want to choose one person, if I had 80 people and I wanted, what's probably I choose one person that one of them is left-handed, there's 80 ways to do that. If I want 2 people to be left-handed, that immediately becomes disgusting. Right? Even with just 5 people, how do I start? I want 2 people. It could be the first 2, or it could be the last 2, or it could be the middle 2, or it could be the first one and the last one. It could be the first one and the second. That is already kind of a large list, yes? Mathematically, every single one of these looks like what? L times not L to the fourth. Mathematically, that's what they all are, correct? So this is L times L not to the fourth, L times L, and when I add them up, I get 5 of them, yes? I like it. Why does this make sense? How many lefties did I want? So that's why there's a 1 power on that. So that means how many not lefties am I going to get? 4. 1 that matches what I'm looking for, 4 that don't. Okay, love it. Where did number 5 come from again? And does that make sense? Because how would I say this? How can I get exactly one left-handed person? I could do it this way, or this way, or this way, or this way, or this way. 1, 2, 3, 4, 5 of those. Okay, I love it. You're all like, okay, dude, proceed. All right, I'm sorry. So now I can actually figure this out. This would be 5 times 0.11 times 0.89 to the 4th. Somebody help me out. What is that? 987,606.3.
0.345.
0.345082.
3451. You guys cool? You guys good? Okay, like it. So what that means is there's almost a 35% chance that in any randomly selected group of 5 people, there's at least one left-handed person. I'm sorry, there's exactly one left-handed person. Any group of 5 people you pick, that's the chance that you'll have one left-handed person in that group. Okay, I like it. Maybe. Okay. Now, let's ramp this up a bit. This, again, these are stupid easy to get. However many of these I want, however many of those I want. That I can always do. The 5 is what sucks. If that list is long, do you want to make that list if there's 18 million of them?
No.
That's a quick no, Jeff. Right? What does our calculator do best? Count shit. Right? It adds stuff. It can count stuff. So we're going to actually use a button in the calculator. This is one time we're going to do that because I'm not going to make us all make a list of 18 million things. You're welcome. So here's a harder problem where we're going to find the one number is going to help us. The one button in the calculator is going to help us. So let's say that 83% of students I don't know what do what 83% of students enjoy popcorn. I appreciate that. My creativity is running low on situations. I just make too many of them. So one thing I'm going to introduce that I should have done earlier, instead of writing, that kind of gets old really quick. What I'm going to do is I'm going to define the symbol small p. That's going to represent the probability of success. And then we're going to use Q to represent the probability of failure. And you'll see why in a minute. So let's say let's say we pick, so from this situation we pick 42 students randomly, right? And I want to know the probability that exactly, what do you got, Jeff? Let's say 34 of them like, or let me say, enjoy popcorn. I don't know why I'm saying like that. Popcorn, cool whip.
Whiskey.
There it is. Cool wheat. All right, let me stop for a minute. You guys take out all the shit we just did. I have 42 students, and I want to know the probability that 34 of them like popcorn. Right? Okay. We're building up to a point. Let me ask you this. I really want you to see what we're building up to, because right now it's sort of like just an exercise in math and letters and multiplying shit. You're like, what the hell is this all about? Has anybody ever been on an airplane? Has anyone ever been bumped from a plane? You have. Has anybody ever heard, if you've never been bumped from a plane, that doesn't mean they're in the air and they kind of like bump you out and you're like, oh shit. So congrats on surviving the fall. But what that means is you're sitting in that thing, waiting to get on the plane, and they come over there and we'll give, either they do this, we'll give $100 to somebody who would give up their seat, so they're asking people to give up their seat. And then eventually they might get to the point where like, we're just gonna bump you because you're bumped off, get out of here. Why does that happen?
They oversold.
Yeah, they oversold. Why would they do that?
Because the probability that people don't show up.
Yes, there is a probability that people will not show up. And if you're an airline, what's the worst situation to be in when you have a plane about to take off? Empty seats. Empty seats. That plane's gonna go. You wanna cram that thing with people so you're making the most money you can from that plane, correct? That's what you want. Since there is a probability that people will not show up, they are going to oversell. I want to know what's the probability that we'll have to bump people if we oversell by this, by this, by this. Why would some airline want to know that kind of thing? What's the probability that we have to bump people given we oversell by so much? Think about it for a minute.
Let the pilots know how many people are on board?
Say again?
Let the pilots know how many people are on board?
No, that they'll just know once they get there. All right, what's up?
Because if they do or if they get to a point where they are bumping a lot of people, it can cost them even more. So they're trying to find that.
True. Okay, good. Plus, it would be bad PR.
Yes. And also-
If an airline suddenly started bumping like 10 people per flight, don't you think that's going to hit the news? Don't you think it's going to probably hurt their bottom line? There's going to be fewer people wanting to get on a plane if I have such a high chance of being bumped off. So they want to find that sweet spot that lives within something that's good for PR, that's at least not bad for PR, but that guarantees they make the most money. Yes? So they want to be able to calculate these probabilities. If we oversell by 3 seats, what's the probability we have to bump people off? Is it too high? Because that we have to give these people something for okay. This is the kind of math that you would use to kind of analyze that situation. Right? What's the probability? Given that this plane has 300 seats, what's the probability that more than 300 people show up? And you know the probability that somebody doesn't show up. Are you guys with me? So almost every business has, so like my friend Sean, when he was alive, he was a financial analyst, and he made stupid amounts of money. But what he did basically was he watched factors and he looked at the price and he would tell them, this is the price you should set this at because it seems to be meeting the demand and this is what should give us the highest profit. And every day, everything changed a little bit. So he's constantly updating his formulas and so forth. And that's why I don't ever want to do that. But that's kind of like what this is leading towards, the ability to do that kind of analysis. Okay. Bless you. So, I got 42 people. I want 34 to enjoy popcorn. So how many little P's am I going to have then? A little P is the product of success, which is enjoying popcorn. So I'm going to have 34 of them. Is that cool? I'm going to have 34 of these. So how many Q's am I going to have? How many failures am I going to have?
66.
No. How many people are there? Oh, that's your facial expression. How many total people are there? 42. There's 34 successes. How many failures?
8.
So these two will always add up to be the total number of things or people. Of course they will, because I'm breaking everybody up into 2 groups, right? Now, there's a number that went in front. Remember the one for the 5? How big would so this could be the first 34 are P's and the last 8 are Q's, yes? Or it could be the first 4 are P's, and then there's Q's, and then there's P's in the middle, and then there's Q's, and then holy shit! Do you understand that list is going to be stupid big? Do you understand that? I have 34 P's, and I want to sprinkle them around every way I can in 42 slots. There's a stupid number of ways to do that. Oh man, let's do this. So, how do I make my calculator do that? If we can get that number, we're golden. Let me do something I haven't done yet. So, if you look at your calculator, somebody got the calculator? Man, what did I'm exceedingly loopy. Okay. So anybody see the new Guardians of the Galaxy movie?
Yes.
I haven't seen it yet. Is it good? Okay.
You'll cry.
Huh?
You'll cry.
I'm gonna cry? Oh, okay,
I
good.
watched the whole thing and didn't cry.
I need
One bit.
I need catharsis. I get into movies, so yeah,
I have no soul.
my friends are always like, Jeff, man, it's a movie. I'm like, Jeff, it's all right. So I probably will cry. Let's see. So watch this. This is kind of cool. There's a button we haven't. I don't think we pushed it yet. That should be really enticing to you. No, even if you hate math, you should be very curious, huh?
It's the red button.
The what now?
The red button.
The red. Oh, yeah, the big red button on the back. Math. It's like somehow they crammed all of mathematics into this one button. So if you hit math, look at all this shit it does. The very first button, real quick, just to show you some of this. Very first button looks like it's something to do with fractions, right? So if I say 856, or 8,500, I don't know, let me make it something it can handle. 856 divided by 924, and I say make that a fraction, it'll give it to me in reduced form, right? If I just type in a 258 and I say make that a fraction, there you go, reduced form, right? Anyway, so back in pre-algebra, you're like, why didn't I know about this? But so hit math. There's other shit down here. I don't care about it at the moment. Right now, I want something about probability. Now here's the idea. The number that's going to go here, I'm all over this. The number that's going to go there has to represent what? Why was the number 5 before? Why was the number 5 when we did that lefty problem? Sorry? How long the list was, right? How many ways there was to choose one person from 5 people, correct? What do I need that to be now? I want to know how many ways can I choose 34 people out of 42. So this is kind of cool. That's all I wanted to do up there. So now watch this. It's kind of cool. That button right there is what we're eventually going to want. Let's not do it yet. Here's why. So I've got 42 people, correct? I want to choose, so not National Public Radio, it's this one. So this means permutations be combined. Basically, the C means choose. I want to choose 34 people, yes? I want to choose 34 positions to put a little P dude. So if I put this in the calculator, let me see if I made something that's too big. Oh, thank God. That is how long this list would eventually be if I made it. What number is that? 118 million. If I continued this list, there would be 118 million, blah, 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 entries in this list. Do you understand? First problem we did, I made the entire list because there's only 5 things. And that's where the number came from. That's where this number comes from, is how long is the list. Because how many of these do I have is how many entries there are, right? So to get this number, it was 5 at first, but to get it for us, it would be 42, choose 34. So in the calculator, I could put 42, choose 34. What was P? 0.83 to the 34th times point. What's Q going to be? Sorry, so P is 0.83. I told us that. What's Q?
Point 17.
There it is. 0.17, 11. So P plus Q must always be 1 because P and Q cut things, right? They cover one's one thing, the other thing's the opposite. So together they cover everything. So this would be how many 0.17s do I have then? 8. 34 successes, because that's what it said. The rest, failures. And by the way, success doesn't have to be a happy thing. It could be finding a dead body. Let's probably find 11 dead bodies in the battlefield. Okay, finding a dead body is a success. So success doesn't mean happy, yay, yay. It means what we're looking for. I like it. So we could be looking for rabid squirrels. I don't know. Normally I'm not. So let's see. I could put this whole damn thing in at once. 42, math, probability, choose, 34, Jeff. Hit the over arrow to come back up, times 0.83 to the 34th. Hit the over arrow to come back down, times 0.17 to the 8th. Let's see what we get. So almost a 15% chance that exactly 34 people out of 42 will enjoy popcorn. Woohoo! Yay!
I have the TI-83, so I don't know.
Oh, yours probably doesn't. Yours looks like this. Let me see. Can this one handle this?
Mine's all whacked out.
Hold on. Yours not whacked out. It's just different. Poor little thing. So yours looks like this. Let me see. 42, math.
Yeah, that's what I'm
Hold on. Like this, right?
Yeah.
All right. 34 times 0.8. What was it? 9? 83
183.
to that. So you're see it like that, right?
Yeah.
So yours, yeah, that's all. No big deal. So you just type it in the same way. You don't have to worry about the over arrow because it doesn't go down. It doesn't go up. It just goes flat line.
I put parentheses around the 42 NCR 32. I mean,
If you want to.
oh, that's what I did wrong. I did 42 NCR 32. Okay.
Oh. Okay.
Oh, okay. Thank you.
Is everybody else all right? Did everybody else get the same number? Okay. Mode. You go back to this. By the way, so if you hit your mode button and you have a choice between these two, this is the one that makes exponents look like exponents, and this is the one that doesn't. If you have an older calculator, you probably don't even see these two things.
Real quick, is it 145? Is that what we got?
1, 4, 5, yeah. One, 4, 5, 9, 6, yeah.
Yeah, thank you.
So 1460. Rounding it to 4 places. Okay, maybe.
I still need a minute to figure this out because I got my T and T tonight. So.
Neato. Good luck. Find a manual, look it up online, something. Yeah, because that stuff I don't know. Okay. So watch how this formula is just a little story. I got 42 people. I want to choose 34 of them to do something. So 34 of them do this. The rest of them do this. I mean, that's right. That's what I try to show students. A lot of formulas, not all of them, but a lot of formulas you can actually just read in English what the hell it's saying. Yeah.
So why do we do the 0.83 to the 34th? Oh, because that's success and failure.
Yes.
Okay.
I love it. Yes.
Where do we get that 0.17 from?
Oh, if the probability of success is 83%, the probability of failure is the rest. So 1 minus that. I like it. So P plus Q is always 1. And these two exponents are always adding to N, the total number, right? Okay, maybe. So let's do one more example, and then I'll give you guys, believe it or not, I got a hand up. Okay, so let's say, right now I'm just making shit up. Let's say that we know 27% of Americans are excited about the next election. Anybody here excited about the next election? Presidential election?
Interested.
There, exactly. So that's why a low percentage. Excited, I don't think many people are excited. A lot of us just want it over. We're hoping, and I'm not going to talk about my political beliefs, but oh God. Okay. Let's have somebody in prison. Okay, stop. So let's say that I pick what you got, Jeff? 56 Americans, and I want to know the probability that. Let me write it this way. That I get exactly what, Jeff? I don't know. 0.3. Let's say exactly 16 that are excited. So first thing I want you to do, and this is what you do in a lot of math problems, let me identify the bits that I need to know. So what is N?
56.
Yeah, 56 total people I'm talking about. Somebody else tell me what is P? No.
It's,
That's X.
It's 16 over 56. Right?
No, definitely not. Come on. Okay, listen. 11% of Americans are left-handed, correct? Is everybody with me? Is everybody with me? If I choose 10 people, have I changed the percentage of people that are left-handed because I chose 10 people? Look at my power. No. What percentage of people up here are excited about the next election? 27%. That's B. Stop for a minute. Do you guys see that? Because that's one of the most common mistakes. There's not a damn thing about this question that would affect the probabilities. Asking a question can't affect the probabilities. Okay. So what's Q?
73?
0.73. Kick ass. Because again, P plus Q must be 1. So whatever P is, Q is the rest of it. This is not where mind your P's and Q's comes from, by the way. Sorry. Have you ever heard of that phrase? Okay. Like, whatever, old man. Alright, shut up. You and your old phrases. Mind your P's and Q's. X is 16. This is the number of successes. So how do I set this up? How would the formula get set up? I got 56 people, and I want to choose 16 of them to do something.
And then you want.
So how many successes?
16.
16. It's a little repetitive, which is nice. I got 56 people. I want to choose 16 of them to be successes. So I got 16 of these. And how many of these? Yeah, these two have to always add up to be the total you had, because you're just breaking up that into two groups. Either you are excited or you're not. So you're one of those two groups. So you can throw all that crap in your form in your sheet, but let me make this into a general formula. What was 56? What's the symbol for 56 in this problem?
And
N. 16 was X.
X.
What was 0.27?
P.
P. What's 16 again? X. 0.73 was
Q.
Q. Here comes the tricky part. How did we get 40?
Oh, it'd be
56
n minus.
N minus
X.
X. Okay, that's the part that trips people up. But all that means is the rest. If I have a total of n, and x of them are doing this, n minus x are doing the other thing. So this is another little new formula. Whee! Anybody plugged in the calculator yet?
Yep.
1133. Neato. Everybody else got the same thing? Okay. Yes. Okay. So about an 11% chance that 16 people out of 56 Americans would be excited about the elections coming. I really want you to see, this is not, you can't just do like, what's the probability I pick a red marble? It's the number of red marbles divided by the total. No, I already know the probability. I'm not calculating the probability a person. I'm trying to use that for a group of people, right? So what I always get is people kind of calculate P. No, they're going to give it to you. They're going to give you what P is. And you can figure out what Q is. You can throw stuff in the right place in the formula. Maybe. All right, so let's do this. Got a little handout. Surprise, surprise. Go ahead and start trying to work on this. Oh, Kevin did it. I'm sorry here for. I just not right here. Oh, okay. I'll put it on the back of this. All right. I don't have a blank sheet of paper. No. I'm going to kind of start catching up to you guys. Kind of gave it all away down here, but oh well. So, by the way, I haven't said this yet, which is really funny. So I'm such a great teacher that here's the name of the thing we're actually doing. These are called binomial probabilities because how many possible things are there in each of the problems we've done? How many possible outcomes? 2. That's the bi part, right? Binomial. That's all it means. And I call those NPQ problems. That's a quick way for me to reference it. So they should be remarkably easy to identify. If I give you a percentage, and then we have a certain number of people, and I want to know, let's probably get 7 of them, that's an NPQ problem. That's a binomial probability problem, NPQ. Let me figure out what NP and Q are, so then I can throw that stuff in the formula. no problem, right? So part A, x is 7. You guys all done part A yet? It's part B where things get weird, but you just got to throw in the stuff here, right? So I got 44 people. I want to choose 7 of them to do something. So I want 7 of them to do this. And I want the rest of them, which is 37 of them, to do the other thing. I mean, that formula is just, to me, it's just so neat. You could just, it just exactly tells the story of what's going on. And then you throw all that business in the calculator and you get something. What do you guys get? 1610? Okay, that sounds familiar.
I got
11? Controversy. I like it. All right, 44. Choose 7 times, not divided times, not divided by. To the 7th times 0.848 to the 37. Oh shit, did I leave somebody out? One 1611 exactly. No. All right. So some of you guys got to be careful. Don't truncate. Don't cut round. Yes. Don't just chop it. Okay. Part B gets strange. The formula is pretty simple. How many ways do you think there is to choose nothing? I don't mean like this. You could do, I don't want any of them. No, thank you. No, I mean, there's one way to choose nothing. You just don't choose anybody, right? Not all the various faces you can make as you do. So there's one. So that's one. How many successes do I want on this problem? None. What's anything to the 0 power? 1. Anything to the 0 power is 1. And then I get, how many failures do I want? 44. So this is 1. This is 1. So actually, I could just do this by itself. You don't have to know that. You can just throw it all in the calculator. But what is 0.848 to the 44th power? Can you be more specific? No, I'm joking. Sorry. Yeah, exactly. What does that e negative 4 thing mean again? Yeah, move the decimal back 4 places, right? So the shortcut is, anytime that's a negative, I just put 1 less 0. So that's a 4. I'm going to put 3 zeros. So 0.000, and then it's a 7 because the next number is a 0. So there you go. Triple 07 is the next level above James Bond. Okay, that's a horrible joke. I don't care. I liked it.
You're not wrong.
All right, so very small chance. And think about it. That makes, if you pick 44 people and 15% of everybody smokes, if I pick 44 people, somebody in that group's going to smoke. It should be really unlikely that I just happen to pick a group that doesn't smoke, right?
Closeted smoker.
Huh?
Big closeted smoker.
Maybe, yeah. But this is supposed to be actual, not just reported. But of course, it really is reported. And then here I kind of, and again, I'm not going to give this to you on a test. You're going to have to know how to do this. But that's that age-old thing about at least 1 is 1 minus none. And we just calculated none, didn't we? So I like doing this kind of thing where I gave you something and then the next problem relies on what you just did. So this is going to be 1 minus 0.777, and that would be 9993. And that kind of makes sense. If I pick 44 people, there should be an almost 100% chance that at least one of them smokes. How you guys doing out there? Okay, not everything probability-wise makes intuitive sense. It's one of the first things we talked about. In fact, I can't believe I didn't do that. I might do it here in a minute. There's 2 things I didn't do that I'm really upset about. I'll get over it. Now, real quick, before we do that, we haven't even talked about these formulas because I never remember to do it before I give this handout. Let's say, I always pick on Shaquille O'Neal, but I don't even know if you guys know. infamously, Shaquille O'Neal could not make free throw, save his life. So let's make he'll say that he made 30% of his free throws. Let's be generous. Right? I have a person who can make 30% of their free throws. If they take 20 free throws, how many would we expect him to make? He makes 30% of his free throws. If he takes 20, we would expect him to make 6. What's 0.3 times 20? 6, right? Let me make sure this makes sense. If a person makes 30% of their shots and they take 20 shots, we would expect them to make 30% of those 20 shots. 0.3 times 20. 0.3 is P, 20 is N. So what's the formula for the mean? The expected value, N times P. So if we have 44 people and 15.2% of people smoke, how many people do we expect to smoke out of 44? Well, what's 44 times 0.152?
6.688.
Sounds familiar? Because I've used the same handout for like 20 years. Maybe not 20. No, I've used this for about 8 years. Okay. Now, the formula, by the way, isn't this the best frickin' formula for the mean we've had so far?
Yes.
If I give you a list of data, you gotta add them all up and then you divide by them. If I give you x, p, and x, you gotta do an x times p of x column and you gotta add it all. This one, n times p, you're done. Beautiful. Here's the one that's a little bit harder to explain. Some of you guys would understand the math behind this because some of you guys have taken some calculus stuff, but I'm not gonna do that. But here's the formula. This is how you calculate the standard deviation for an NPQ problem. So it'd be the square root. Jeff, you got to actually, there you go, buddy. N times P times Q. I don't know, 2.4. What is it?
Or 2.382.
2.382? That sound right? Scheisse.
What did you do wrong?
Huh?
You said Scheisse, so that's
Oh, yeah.
wrong.
No, I just hit the wrong button. Yeah, it's 2.381. You were right the first time. Because the next numbers are 4, right? I think.
Well, there's a 7 there, so it's like
True. But again, is that closer to 0 or closer to 100? The 47. Is 47 closer to 0 or closer to 100? There you go. That's why you don't round up. Yep. This is not like dominoes. You can't. It's not a 5, but you're like, oh, it is a 5. No. Okay. Everybody with me so far? These are the most beautiful frickin' equations we've had yet to find the mean and the standard deviation. Kicks so much ass. And then I can ask you this question, which I kind of prepped you for earlier. Where does unusual start? 2 steps up and down, right? So if I put the mean in the middle and I take 2 steps up, holy crap. If you're telling me that's the same, 2 steps down. Jeff. Okay. Let's see, what is that, like 4.7? That's like 11.3? Is that right? Roughly? Nobody's going to help me. All right. I think this is like 0.9 or something.
9.069.
9 point... Oh, 0.9. Is it, if you add 2 of these, don't you end up at roughly 11 point something? Is that, can anybody verify? I'm gonna go crazy. Thank you, man. You guys with me? So all I'm doing is I'm taking 6.688 and I'm adding 2 of these. So it's 11.45, so I was close. I was just trying to do it in my head real quick. 11.45, and if I do 6.68 minus that, I get 1.926. Oh crap, I was really far off. 1.926. did I do? Oh, that's smart, Jeff. Okay. That is the usual values. If I pick 44 people, I would expect anywhere from 2 to 11 of them to smoke. So if I picked 44 people and I saw that 15 of them smoked, would that be unusual? Where's 15? It's up here. So would that be unusual? Oh shit, yeah. It is further away from the expected, the average, than normal. That is unusual. So we officially call anything that is more than 2 standard deviations away from the mean, we call those unusual. Unusually tall, unusually short, unusual number of people that smoke, whatever. Okay, maybe. Later this semester, we're going to realize that unusual might have to start at a different place than 2. If I worked in a nuclear power plant, I don't know if I've told you this story before. If we worked in a nuclear power plant, would you sit there watching the little gauge and it goes from green to yellow and you're like, I don't worry until it gets to red? Or would you get off your ass the minute that little gauge went into the yellow?
Yeah.
So your definition of unusual would be less than 2 standard deviations away. Normal procedures, the minute it starts to get a little bit away from that, I'm off my ass. I'm like, what the shit's going on? Right?
What if it's in the green and it moves up just a hair? Then
That'll probably fine. The minute it starts getting close to that yellow, that's when I'll get off my ass.
Hey, who knows? It could be Chernobyl if I don't move anything.
Oh boy, all right, let's not go there. Or maybe Godzilla comes, you never know. All kinds of bad things can happen. Anyway, so this is what I mean when I say, would it be unusual to find this? You have to actually calculate what's 2 steps away, and then you can tell if it's unusual or usual, if it's expected. Real quick, 2 things. Let me do one of them, because there's not enough people here. 2, 4, 6, 8, 10, 12, 14, 16, 18. A couple things I forgot about probability. There's only 18 people here, but there's still a chance. If you have about 34 people in a room, there's a really good chance, better than, actually 34 I think is a really high chance, that 2 people will have the same birthday. 18, there's still a decent chance. Have you ever heard of this before? So if I just said, what do you think is the chances that 2 people in here have the same birthday? I'm almost certain most of you guys would say not a very good chance. And I don't know, for 18, oh shit, I used to know some of these. So it's a higher probability than you would think, because we think about ourselves. Nobody's got my birthday, but how many pairs of people are in this room right now? How many pairs could you make? All right, him and him, him and him, him and her, him and him, him and her. Yeah. And then I haven't even gotten to you and him. And I'm not even over there. Holy shit, there's a ton of pairs of people, which increases the chances that some pair have the same birthday. So normally when I have about 40 something in my class, I'll say, where's my January babies? And I'll have them right there. Like, I was born September 21st. Anybody September 21st?
The day after.
22nd.
Yeah.
Holy shit. I saw your hand going, like, really? And I always disqualify if there's any twins or anything in the room. I'm like, we'll leave them out because that's kind of cheating. Anyway, so we're not going to do that because I'm almost certainly it's not going to work. Yes?
Like cluster of, months or period tend to be more affect that too. Or like that
Yeah, there's clusters of months. Yeah. Why do you think that might be? Like September is a pretty standard month for people to be born because 9 months before that, in a lot of places, it was really cold, for example, right? All right. So, the other thing I wanted to talk about, have any of you ever heard of the Monty Hall problem? Does anyone know what Monty Hall was?
Yes, I do.
All right.
Sorry. There are 3 doors. One door, the probability basically would be 1 door will have a brand new car in it, 2 doors will have nothing in it.
No. 2 doors will have goats. Okay, so back in the day, so I think it's Wayne Brady who hosts this Let's Make a Deal nowadays. And you don't watch that show unless you're homesick or something, but there's 3 doors. So at the end of the show, they'll have the people that won a lot of money, and they'll say, you can turn the money back in for a chance at $50,000 or something, or brand new car or something. So real quick. Behind one of these doors is $50,000. Behind the other 2 doors are goats, and we're assuming you're not here to win a goat. You're not going to get it. I want a goat, yeah. Right? You with me? Everybody. Somebody pick a door, please. 2? Okay, so I've gotten door number 2 picked. What's the probability that you picked the winning door? A 1 out of 3 chance. What is the probability the prize is actually behind one of the 2 other doors? There's a 2/3 chance that the prize is back behind one of those 2 doors, right? I'm the host. Now, in my head, I've already picked the door where the prize is. You might have got it. Everybody with me? He picked a door, and then I go, all right, behind door number 1, there's a little mutant goat. There's a mutant goat, right? Do you want to switch?
Stay.
Do you want to switch your door? The mistake people make is you think there's a 50-50 shot and you're completely wrong. Why did I open this door? Here's the reality. Are you going to switch?
Nope, stay.
You're going to switch?
I'm gonna stay.
Okay. You won! Woo! Right? Goat. Even more mutated goat. It's got wings. All right. It's a bumble goat. Okay. Sorry. No, watch. This might not make sense. But again, there's a 2/3 chance. I opened that door. Why did I open that door? Because if I open that door, the game's over. The show's over. That wasn't very exciting. I want to get to a point where you have to decide to switch or not. So let's do this. What if there are 100 doors? 100 doors. Right? This is 99. This is 100, right? 1, 2, 3. I picked door number 47. What is the probability I got the money?
1 out of 100.
1 out of 100 chance. Yeah, they're 1,000. It's almost definitely sure I did not pick the money. Then the host says, oh, that's a very interesting choice. And he opens up every other door except for door number 2. Every other door he opens up and shows me a goat. Goat, right? What is more likely? That I picked the right door or that he did not open that door because that's where the money is? What's more likely? That's where the money is. That's why he didn't open that door. There's still a 99 out of 100 chance the money is here. There still is. He knows everything. So when he opened all the other doors, it did not change the probability that the money is not here. It's still 99 out of 100. So here, there's a 1/3 chance you get it at the beginning, but there's a 2/3 chance you didn't. So when he opens the other door, there's a 2/3 chance. So if you change doors, you've doubled the probability you're going to win. I know there's a very high chance many of you guys have no idea what just happened, right? And this perplexed people forever. But if you think 100 doors, it becomes really obvious. Well, the only door he didn't open, that must be where the money is, because there's only a 1 out of 100 chance I picked the money. That must be where it is. There's a 1 out of 100 chance that if you switch, that was the wrong move. So of course I'm gonna frickin' switch. I increased my chances by 99 times to win. Over here, it's just increasing it by double, but still doubling is pretty damn good, right? Has anybody ever seen the show Mythbusters?
Yeah.
All right. Way back in the day, they actually constructed a set. They actually had real people come in and play, and they kept track, and they actually showed empirically that it was double the amount. The people that switched won about twice as much as the people that didn't switch. It's a really cool show. They talk about controlling variables. They talk about all these things when they actually set up an experiment. They also show that elephants really are not afraid, but they're very careful on mice. It's an old thing from like old cartoons. And they were really surprised, as I was, that it's actually a true thing, right?
Oh, you say mice?
Mice, yeah.
Oh.
Rodents of some kind, yeah. All right, that's plenty for today. I'm sorry, guys. I went off the rails there. But so next time, again, what's happening tomorrow? No class. I love it. We'll talk about when the next quiz is. We'll talk about that on Wednesday. And of course, I'll have some time. I'll think about when the next test, if I'm going to move it. I might move it to the 6th. I'll think about it. I'll let you know. I think we should be on track, though. unfortunately for you, for me to move it, but we'll see. Okay. So let me know if you have any questions, and don't forget your stuff if you gave me some stuff.